Good afternoon, good morning, viewers, wherever you are. Thank you for joining us today. This webinar will be recorded and will be available on our YouTube channel in the coming week. Remember to post your questions in the Q&A section at the bottom of your screens. Kindly follow us on our social media platforms so that you don't miss any of our programs. Our handles are CGC Nairobi for both Twitter and Facebook. Without further ado, I would now like to hand over to our director, Dr. Murugi Dirango, to make the welcome remarks. Dr. Dirango.
Thank you very much, Pauline. Welcome, everyone, and thank you for joining us for today's webinar on how remote sensing can be of value to the energy sector. My name is Murugi Dirango, and I'm the director of Columbia Global Center in Nairobi. CGC Nairobi is part of Columbia University's global network of centers aiming to create opportunities for research and scholarship. The Nairobi Center serves as a regional hub for research and collaboration as part of Columbia University's strategy to achieve a global presence. It links the African continent to Columbia's scientific rigor, technological innovation, and academic leadership. I am delighted and honored to introduce you to our panelists today. Professor Vijay Modi is a professor in the Department of Mechanical Engineering at Columbia University and a member of the Earth Institute faculty. He graduated with a PhD from Cornell University and did his postdoctoral work at MIT. Professor Modi's areas of expertise are energy resources access, energy planning for access and renewable integration, demand estimation, and the role of novel payment systems in breaking barriers to upfront costs. His laboratory, the Quadratic Sustainable Engineering Lab, has been responsible for innovations such as a low-cost lead-acid discharge circuit for solar lanterns, fully digital pay-as-you-go mini-grids, battery-less pay-as-you-go smallholder irrigation systems, and widely used tools such as Network Planner for making technological choices under demographic, demand, and geographical variations. Finally, a free open source app called FormHub used over 1 million times for assessing field data. Today's webinar features 2 of Vijay's students discussing their research and more specifically discussing their research in the region. I will now introduce the 2 students. Simone Fobe is a 5th-year PhD student in mechanical engineering. Her research interests are at the intersection of developing low-cost energy monitoring devices and data mining to improve electricity provision services in Africa. After her BS in environmental engineering, she obtained her Master of Science from Stanford, which laid the foundation for her interest in energy systems and IT. Prior to joining the PhD program at Columbia, she worked on energy and healthcare projects at IBM Research Africa, Nairobi, Kenya. Jack Bott is an engineer currently focused on embedded control systems for solar mini-grids and computer vision at the Quadratic Sustainable Engineering Lab. He has an MS in electrical engineering and a BS in mechanical engineering from Columbia University, as well as a BA in physics from Bard College. Jack has field experience deploying control systems across Africa. I will now call upon Simone to start off today's talk by giving her presentation. Welcome, Simone.
Thank you for having me, Murugi. I'll go ahead and share my screen. Okay. Hi, everyone. Good afternoon to everyone in Nairobi. I'm Simone, and I'm a PhD student at Columbia University. My supervisor is Vijay Modi, as mentioned. And today I'll be sharing about our work on predicting levels of household electricity consumption in lower access settings. So this work is done in collaboration with UMass, HERS, RIT, CMU, and that's been under the eGuide umbrella funded by Rockefeller. So remote sense data covers large scope. And in this particular case, I just show a few examples where we have nighttime lights data that is just lighting over the world. We have Sentinel, that's slightly higher resolution, 10 meters, and then we have Maxar at 50 centimeters resolution. Each of these types of data can be quite attractive because they support scalable analysis of varying phenomena, be it agriculture or electricity access, which is our case. We have been focused on using remote sense data, especially in data constrained regions, because it allows us to combine that information with on-site, a smaller on-site observation to make inferences at scale. And today I'll be sharing how we do that specifically for electricity access planning. So in the case of electricity access planning, it usually looks quite standard from a centralized grid perspective. We generate electricity at some sources. For example, in the case of Kenya, we have geothermal. At Okaria, we have possibly some wind farms. The generated electricity is then transmitted through some high voltage lines, stepped down through, and then further transmitted through medium voltage, at which point it can be distributed directly to industrial customers or taken to the household level to offer electricity to individual households. For this planning process, the distribution cost, which is really the extension to individual households, makes up a huge fraction of the cost to connect and electrify people. And they're very interesting alternatives that are gaining more traction in the case of mini-grid solar home systems. So our work is really about how do we match these new technologies combined with centralized options with individual customers based off of what they would consume. And to do that, we need to have some way of estimating how much electricity people would use upon connection. And we're hoping that by doing a data-driven matching process of technology and customers, we can actually support electrifying more people given the same investment. So the question again, like I mentioned, is that we're trying to get at is how much electricity will people consume or use upon electrification? And that's really determined by what appliances they have, be it TV, a fridge, or what they're going to be using it for. Is it in a store where they have cool drinks, or for like agriculture purposes, irrigation? So to estimate how much electricity people would use, you can go through carrying out extensive surveys, but at scale that can be quite expensive, or it can be done through assumptions either based off like population centers where people are located, or energy providers can just also use their experience. For example, in a utilities case, use this experience of how much electricity people use upon electrification. And our work is really looking at how we combine remote sense data with, say, the energy provider's experience to start to answer the question of what people would use upon electrification at scale. So our research question, if I may simply state it, is given today's information, and that information may sit in the form of, say, a satellite image, can we estimate levels of consumption upon electrification for households? So in this case, I show a satellite image. We have a number of structures in there, and we want to say how much will they use when an electricity connection is made. We choose levels of consumption just because it makes the task a bit easier when we use it with remote sense data. Okay. So a bit of background, we've collaborated with the utility in Kenya to understand how people consume electricity upon connection. Our general studies looking at about 100,000 customers show that people first grow their consumption, and then at a certain point, they stabilize in terms of what they're using. So we define this as the stable phase, and we want to be able to estimate what someone would use once they enter that stable phase. We've defined it as about 12 months after a connection is made, and we want to use satellite imagery to make that estimation. So even though we have a way of getting, say, the average or median kilowatt hour that is consumed, we still need to be able to translate that to levels of consumption. So having obtained, say, an average kWh of electricity on a monthly basis, we then take that value and convert it to bins or levels of consumption. At the top here, I show e-guide is our levels of consumption as low and high. And I also show how that aligns with, say, the multi-tier framework, which is commonly used by energy practitioners for decision making. So again, I think it's worthwhile for me to emphasize that the task that we're trying to get at is a consumption prediction task, not a consumption estimation. And what really is the difference? So consumption prediction is saying that we want to look at the information that we have today to predict what will happen tomorrow, say upon electrification, versus consumption estimation, which says we look at today's information to estimate how much electricity is used today. So the consumption prediction task is actually a harder problem, but we are able to make some segue in that space. To do that, still again in collaboration with the data that we receive from the utility, Kenya Power, we're able to prepare that data to get building level consumption. And we, at an initial pass, just look at single customer buildings, estimate their stable electricity consumption in kilowatt hour, and then convert that to levels of consumption. We can then combine that with satellite imagery at high resolution, so 50 cms per pixel. And we ensure that the images that we select are images that occur prior to when an electricity connection is made. By doing this, if I say strict matching process, we dwindle down our data set to about 27,000, slightly more than 27,000 customer image pairs that we can use to train our models for prediction. In terms of our predictive model, at least a V1 version is we take an image, we pass it through a series of convolutional layers. In this case, it's quite dense. And then at the end, we are outputting a probability that the structure in that image is going to be high consuming or low consuming. At the bottom, I just show some activations, like what the model is focusing on, and I'll go a bit more into why that's relevant in our case. We apply some standard, if I may say, machine learning approaches of like data splitting and parameter optimization. So how we choose our image size, how we build our custom model, the learning rates to ensure that we are actually learning relevant features from images. By doing this process, we obtain a performance of around 0.64, which means practically that around 2 out of 3 times we're able to get the right level of consumption given a building in an image. So what are we picking out when we are trying to get at levels of consumption? To the left, I show correctly predicted levels of consumption for low consuming structures and images. And then to the right, I show correctly predicted levels of consumption for high consuming buildings in the image. And what we are observing is that when we're making or when our model is predicting high, it's really focused on the building. That's what gets activated in the model. That's what it's correlating with, that level of consumption. Whereas when we're making the low levels of consumption, it's associating or considering the context a lot more than just the building on its own. Okay. So having trained our model in Kenya using utility data or consumption from actual meters, we are able to extend this prediction for the whole country. So using about 12 million structure locations in Kenya, we're able to predict levels of consumption by taking corresponding images for those 12 million buildings and putting them into our model, our trained model, to output the levels of consumption as shown in these examples. Here I present sort of like a summarized version of those predictions, and for a few reasons. One, we're able to see that, at least for those familiar with Kenya, that our urban centers are coming out as having, sorry, before I actually say that, let me explain the figure a bit more. So here, blue shows places that have a lot of low consuming structures, whereas red shows places that have a lot of high consuming structures. So we are able to see that our urban centers are tilting towards having higher levels of or more high consuming structures. And then as we move away from those urban centers, we're getting rich predictions. For example, in the highlights here, you can see that we have a mix of like low and high in that range. So we're getting rich predictions at high resolution. So these predictions can be accessed through our API, and you can visit the link to interact with it. Not going to spend too much time on that here. So we thought it was quite important for us to verify our predictions with externally collected surveys, external data. And one of those data sources is the World Bank's multi-tier framework survey. That survey is a nationally representative survey of both electrified and unelectrified households. But we focus specifically on the electrified set because it records on average how much electricity households are consuming. So by aggregating the MTF survey at the county level relative to our predictions for residential customers in Kenya, we observed that we get good agreement with what the survey is recording versus what we predicted. And this is weighted for sample size. So this is quite encouraging to us that our approach sort of starting to tease our consumption patterns, and we're doing that at scale. So going beyond just data and satellite images, we've considered other data sources that might be of interest. Some of them remote sensed data, some census indicators, some are our own metrics, for example, proximity to key infrastructure that might be relevant in prediction. So we wanted to evaluate how helpful these would be in improving our current baseline approach. So the census in Kenya provides data at the ward level. At least the 2009 census provided data at the ward level, and it gives percentage of the ward that say has surface versus improved versus unimproved water, and it does this kind of approach for subsequent indicators. So we use those indicators to see if they can be helpful in augmenting our predictions. We also use, like I mentioned, nighttime lights, which is also remote sensed, and some other metrics or indicators that we derive, say proximity metrics. So by combining this, what I'll call non-visual features with our image model, we want to be able to see how helpful they are in getting better performance, but what we learn from the types of predictions that they help us to make. So here I just kind of show a snapshot of our results on the different combinations of this, but I will talk a bit about a few things. One of them is for the purpose of electricity planning, not only is it important to get it correct, it's also important to maintain the spatial variability in the predictions, meaning that if you have 3 or 4 households in the same area, you want to be able to differentiate the households individually in terms of what they're going to consume. So by using, say, census indicators that occur at a ward level, even though the overall performance might look comparable to what you see with visual features from images, the actual variability in predictions at the ward level is non-existent, meaning that we are, by using those census indicators, the whole ward will be assigned to one particular class, which is not realistic. We do observe that the images actually offer the richest predictions, where they preserve the diversity of consumption levels within geographic areas and still try to push on the performance end. We get a bit of a boost by combining everything, but the main takeaway is actually finding data sources that match the resolution of the images and that can preserve that geographic or spatial diversity in predictions. So just to step back a little bit and sort of like summarize what I've shared here today. One, the task we're trying to get at is quite difficult of a task for multiple reasons. We're trying to predict the future given today. I'm sure you guys, that's a very difficult thing to do. Also, we're trying to predict consumption levels. So electricity in itself is not necessarily evident from satellite images, and we're just trying to use proxy indicators in satellite images to make that prediction, which also makes the task hard. Nevertheless, as I've shown, daytime satellite imagery holds relevant features for predicting consumption levels, where buildings get highly activated when we're predicting high consumption levels, and then the context is more, it's considered more when we are predicting low consumption levels. We also observed, and it's not necessarily shown in this presentation, that learning about buildings independently first actually helps with generalizability and tuning to the task at hand. In general, additional data can be helpful, but you have to be quite thoughtful about the resolution of that data and the implications for the problem that you are trying to get at. So going beyond Kenya, we are actively doing transfer learning, which means that we are testing our Kenya model on other countries, say Rwanda, and also starting to build models in other countries, say Rwanda, and testing their performance in Kenya. Ultimately, we want to have an approach that allows us to sort of get a sense of what people consume across the continent upon electrification in a robust way. And we're looking to collaborate with utilities, energy planners, decision makers in either like developing these tools or sharing the outputs from our models. So I think that's sort of all that I have today. Thanks for listening, and I will hand over to Jack.
All right, thank you very much, Simone. Thank you for having me at this conference. And so I'll start by sharing my screen. All right, so first of all, my name is Jack Bott. I work at the Quadracci Sustainable Engineering Lab under Vijay Modi. And today I'm going to be talking primarily about 2 projects that I've been working on at the Quadracci Sustainable Engineering Lab, focusing more on one, which is called Irrigation Detection by Car. And in that project, me and fellow grad students put together a computer vision and sensing system. So a small unit that does computer vision and takes in sensor data, and from that detects and geolocates irrigated and non-irrigated farmland. So that's kind of the goal of that project. So collaborators in that project were Weifan Zhang, Vivek Kumar, Nihil Mehta, and our lab director, Vijay Modi. And we were able to present this project at the Global Humanitarian Technical Conference in the fall. You can find that paper on our website under publications or at IEEE if you search GHTC 2020. So first, I want to talk about the background motivation for this project, and I'll start by talking about irrigation and how it's necessary for horticulture, and then horticultural crops are more valuable than rain-fed crops. So we know from some of our other projects, I'll mention a project called Acacia Irrigation, which was set in Senegal, where we installed some irrigation systems, and we discovered firsthand through that project that installing these solar irrigation systems led to our farmers, our smallholder farmer beneficiaries, increasing their yields and being able to add additional growing seasons. So we saw firsthand the benefits of installing these types of irrigation systems. And so through the Irrigation Detect project, we seek to provide data, specifically the geolocation of irrigated and non-irrigated farms, what is existing right now, and in the aim of showing the potential market for installing irrigation systems and encouraging the investment in it so that we can get the benefits. The pictures on the right are of one of the farms that, one of the solar systems that we were able to install and some of the produce that came out of it. Digging a little bit more into Acacia Irrigation, the physical installation of the solar irrigation systems, we were able to install 3 pilot systems in 2016 in Gabar, Senegal, which is in the Niayes zone, which is the coastal region of Senegal. Those 3 systems served 21 farmers, so we were experimenting with increasing utilization of the system by sharing a central solar load. And a lot of the farmers that we were impacting were transitioning from either using manual watering techniques, so lowering a bucket into a well and distributing it around your farm. You can imagine how labor intensive that is. Or using inefficient gas-based pumps where fuel that was intended for boats was mainly used, and just so sort of not environmentally friendly, expensive, and just kind of unpleasant techniques to an electrical irrigation technique, which just has a lot of convenience factor to it. So we've seen years have passed. Our pilot systems are still working there, still serving people, and we've also seen one of our someone that we worked with there has been able to start a company installing single use, or not single use, but single farmer systems in the area, and he's sold over 100 in the immediate area. So this is kind of picked up as an idea. The pilot systems were encouraging for farmers in the area to kind of show that solar irrigation could work, and then show the benefits of it. So it's been popular. This is, so just to show a little bit more about it, this is an aerial view of that. So those farms are all very close together. You can see the red, green, and kind of light blue are the 3 different groups, and each one is highlighted. And you can see in the center a road going through. So this will kind of harken back to what the other project, the Irrigation Detect, is that how close these irrigated plots or farms are to the road within visible range. You can also see just the yellow is the solar installation. So they were located in the center of the different plots, and wires were distributed out to those farms. So getting back to Irrigation Detect, we know we want to collect data, and we know why we want to collect data now. So how do we get the data that we want? We could look at existing published data sets, kind of concentrate data that's already out there and publish it. but we decided that there wasn't enough. We could look at satellite data, as Simone said, which is extremely valuable, and I think what we're going towards. But to make satellite data, most satellite data worth it, you need some sort of ground truth. You need some sort of proof on the ground to extrapolate to your satellite data. So we know we need to collect some data. As Simone mentioned as well, one of the primary techniques for this is collecting individual on-the-ground surveys, but it's prohibitively expensive. So we were trying to explore in this project alternative means. So we thought about drones, but they're expensive or still relatively expensive, and you need a dedicated person to control them. So we wanted to do something that was more passive. So we decided a car-based system would be good, and designing the system so that whoever's operating it doesn't need to have too much user interaction. You just stick it on the car, plug it in, turn it on, and you're good to go for collecting data for the day. So I'm going to continue talking about that system that we decided to design. Conceptually, if you look at it a little bit more, the idea is you have the road traveling down you're traveling down the road in your car. You're the red dot here, so you can capture your GPS location with a sensor. That's pretty standard. And then what else do you need to know to get the GPS of a feature that's in view on the side of the road? So you potentially need a camera view from the side of the car. So that would be, facing out to the outside of the car, outside of the road, so you can see the object in view. You need the orientation of the car so that you can get the vector from where you are to the feature in view, the feature of interest. So you need maybe some orientation sensors, or you can get that data from the GPS sensor, and then you need the distance. So how do you get the distance? Two main techniques for this that we explored are LiDAR or stereo vision. For our project, LiDAR, the systems that are available are prohibitively expensive, so we went with stereo vision. Stereo vision detects or estimates the distance of objects in view by having two cameras positioned at a known distance apart and known characteristics of the cameras. And then you can see, if you look in the frames that are captured, you would see one object in one view and the same object in the other view, and how much are they shifted from one frame to the other. So what's they call it the pixel, the disparity from one to the other. And that gets smaller as you move further away as the object in view gets further away. So we're capturing the GPS, we're capturing the orientation, and through that through stereo vision, we're capturing the vector. And so we can extrapolate the new GPS coordinate of interest from the GPS coordinate of the car traveling down the road. And that's our ultimate goal, is to get those GPS coordinates of our features of interest, export them to a CSV, and then be able to overlay them on satellite data. So to kind of go through that in a different way, we need to record data. So we need to store it locally on the device. And then we need to upload it later, because there probably wasn't 3G or 4G or what have you in the car. So you need to take it back so you can upload it to a cloud interface. Then you need to tag the images. You need to go through frame by frame and figure out what's available there that is of interest. For us right now, we're doing that manually, so you need some way to do that. Maybe you could do it with some sort of machine learning afterwards, but start with manual. And then you need to calculate the distance. Once you've selected your features of interest, how far away are they? Then correct the GPS coordinate from where you are to that feature, and then overlay it on satellite imagery and use it as a quasi ground truth. We understand that it is not as accurate as survey data, but you would be collecting more, so it may balance out. So that's kind of the idea. what's the hardware architecture that we're using for this project. We decided we wanted this to be as cheap as possible. You could have as many as possible. So under $500, and we're going off an open source Raspberry Pi based system. So we used a project called Stereo Pi, which is based on the Raspberry Pi compute module, and basically it just allows 2 cameras to be attached to the Raspberry Pi, whereas one would be the typical application. We have a power system with a battery backup that connects to the cigarette lighter in your car. So that's in pretty much every car, so widely compatible. And then we have our GPS sensor, we have our orientation sensor. The orientation sensor is a mixture of a magnetometer, an accelerometer, and another sensor, and they all come together to this Bosch sensor comes out and gives you an orientation. And then we wanted to add a real-time clock because we want to cross-reference the sensor data that we're getting with the camera data that we're getting, so that we can take those 2 inputs and recompute the GPS coordinate. And so a closer look at the prototype that we're using now. It has all those components that I mentioned. It has the power comes in, it charges batteries, and then it boosts up that voltage so that you can power your semi-power hungry Linux computer with all the sensors involved as well. And we're positioning our cameras, so you can see on the left image, the unit itself, the prototype unit itself on top of a car for data capture. And the cameras are exactly 200 millimeters apart. And that is a larger distance than normal for this kind of thing. And that's because we're shooting for a much further distance than would be typical for, say, a robotic application or autonomous driving sort of application. So we'll get into that a little bit more later. But to break down the software pipeline now, the steps you need to go through, or we decided you needed to go through to do this, are first you need some pre-processing. You need to come up with a mathematical model for the cameras. We chose to use fisheye cameras because they will give you a almost 180-degree view of the landscape, so you capture more of it. But fisheye cameras distort the view towards the edge of the frame, so they need to be rectified. So they need to be undistorted so that we can do our depth detection. So those 2 processes need to be set up for the prototype, and then we need some sort of GUI or some sort of application to go through and identify what frames are of interest once we've captured a large amount of data. If we're videoing all day, then we need to have some sort of method to go through and do that and tag the images. Once we know what images have features of interest, we can produce a depth map for that image, and then we can match that image timestamp with the sensor output, and thereby be able to extrapolate the GPS coordinate of what we're interested in, so that we can get our end result. This is a depiction of our GUI, our user interface, that we use for going through the frames and picking targets of interest. So you can see in the left frame, there's a red dot, and that is a selected target of interest. We'll come back to this kind of view, or we've already looked at this view in the concept sketch, but we'll come back to it again. So there's a scroll bar at the top. You can go through each particular frame, skip through them. We have an auto tagging feature, but regardless, you would select features of interest, and then you would know what you would be able to process at the end. So as simple as possible for that sort of user interface. This is a depiction of the stereo depth estimation. So you can see left and right frames. You can see a black arc on the top and on the top of the left and the bottom of the right, and that's from the rectification of the fisheye lenses. But if you look at, say, the table in that frame, you can see it's slightly over to the left more in the leftmost image, in the leftmost capture, whereas it's a little bit to the right in the rightmost capture. So there's a known baseline disparity, which is the distance between the cameras, but then there's also a disparity that comes from an object being further away. So that's that disparity is what creates the map on the colorful map on the far right, and that gives us an estimation of the distance. And so here's our overview again. We saw the view of the cameras facing out towards the vector that's going from the red dot to the pink dot. And so this is just another view of that. So how have we done so far? We have had less than 9% error for objects up to about 10 meters. We've gone a little bit beyond that, but our prototype unit so far is capturing at a pretty low resolution, 1280 by 480, and that's two images next to each other. So really it's 640 by 480. This is pretty typical for the processing power of the Pi, but it's not far enough for our application, of course. So we need to kind of next steps are, or things that we've been working on are increasing the resolution of the camera and increase. So basically, the reason the resolution matters is because you're looking at a disparity from one to the other. So the increment from one to the other is the pixel size. So if you have more pixels in between, you can get a more accurate distance. Or in our case, we're kind of maxing out the number of pixels. You might get down to 8 pixels in between, or 1 pixel in between, and that you can't go any smaller than that. So you need more resolution. So with our current cameras, we can go up to 5,120 by 1920, and that's a 4 times increase. And we can do that by capturing still frames instead of video, because the still frames, you can't re-encode the video fast enough. So still frames are better, but you capture that, capture the timestamp of that, you get much more pixels, and then you can get a further range. So if that doesn't work, we have sort of other, or if it's not far enough, there's higher quality cameras that we can use, and then we could also consider increasing the actual physical distance between the cameras. We could probably go up to 1 meter, which is another 5 times increase, without kind of blocking out your standard car is less than 1 meter long. So those are some things that we're looking at, and kind of the error rate that we're looking at. Other opportunities, so we're already capturing this video from the side of the road. We're looking at irrigated plots, which you can see from the road. We're looking at, you can see this image on the bottom right, irrigated cabbage plot that you can see from the road. You can identify that as a human. Other things you might be able to see are power lines, wells, other kind of pumping infrastructure, and things that of the nature of at least power lines would be much easier to pick up in a kind of automated way. So there's other opportunities to explore with this kind of street view imagery data collection that were kind of possibly next steps. So what we're going to do next, increase the resolution, try to increase that distance. We're currently we have our affiliate Marcus Walsh in Tanzania testing out a unit right now. So we're trying to get more realistic for our application images, so we can get how far do we need to really detect, what kind of hardware increases do we need to make, and just kind of to go back to, we're trying to output this data of features of interest that we're seeing, so we can overlay it on satellite imagery and take it back to that. But thank you for your time. Thank you for listening, and that's all I have. So I'll stop my share and let Vijay take it back.
Oh, that was really wonderful. Thanks, Simone and Jack. Um, Pretty much that's the main presentations. I'm here to just give a little bit of context. Um, is some of this my laboratory's first engagement really started in Kenya uh, with the then PS, Patrick Nyoike, uh, asking how we can do planning of electricity rollout better. And so it was quite fascinating and um, tremendous collaboration at that time when KPLC went out over a single summer and mapped out all the power lines in Kenya within a couple of months. They had not been mapped before, but this was back uh, close to 15 years ago. So that work started in Kenya with the then PS, and we helped develop some of the support tools that KPLC needed. And that work showed that if you do one home at a time, things can be quite expensive to connect, and you could literally, the wire could just go over someone else who could have been much cheaper to connect. But if they had asked individually, each one every 6 months, things can add up, as opposed to just thinking through systematically across the landscape. And so that, I just wanted to close the loop there, that's where it started. And so now with Simone, also first working with Kenya Data in collaboration with our colleagues at UMass, at RIT, it's really, things have come together. And I think uh, one poorly understood factor for utilities has been to think about, how can you appropriately develop wire standards, based on what you know uh, about potentially future consumption, fraught with uncertainty as it is. So that's, and I think the point I wanted to make there also is that the commercial departments of utilities actually are poised to help themselves. And we are here, Simone is here, who actually lived in Nairobi as well, to help utilities do that. And the other point I wanted to make was that there are many sources of consumption in rural settings. So I just wanted to show one slide, perhaps. This is from Uganda, just in a small area. And, of course, same thing applies to Kenya. And, the household clusters are shown as gray circles. But there are many, many other loads in that same community. This is about 100 square kilometer community. And this is even without the presence of mechanization in agriculture. These water pumps that are shown here are actually for drinking water. And early estimates were that actually these loads could swamp household loads, but now we are adding to that the agriculture loads of the kind that Jack showed. So this is just the beginning. In many other countries, I'm originally from India, some parts of India where really the green revolution took hold, uh, you know, energy and electricity were critical to make it happen. So our next phase of work, which hopefully through these webinars we can highlight, is how we are working on detecting agriculture using remote sensing, detecting those few farmers that are present in the landscape. Uh, Through the e-guide effort, our colleagues at Colorado School of Mines are furthering how night lights can be used. Um, our colleagues working with Simone and others on their own. Bob, you mentioned Simone is looking at commercial consumption as well, business consumption. So I think the point I wanted to make is that how can we form a supportive system to synthesize some of these things, whether it's markets, whether it is businesses, whether it's drinking water or irrigation, whether it's households and schools and clinics. And this is one vector along which we are working. And hopefully we can have a couple of such seminars. And thank you to the Columbia Global Center in Nairobi to reach out to the region to enable such an opportunity. So I'll stop there, and this is the first of these webinars from our lab, and hope to do more. And if there are any questions, put it in chat, and we can go from here. Otherwise, if there are no questions, or we can also close, but let us know. And while others may not have as many questions, maybe I can just pose a question or two to Simone and Jack. Okay. So Simone, any thoughts on what are the sort of what are the issues of consumption growth over time? How does that connect with satellite? You mentioned the prediction versus estimation. Today, of course, the utilities are interested in those who are not connected. How should they, on a pragmatic basis, use your work? Any thoughts on that?
Yeah, so you hinted a bit at it earlier that utilities are placed to answer these questions, mainly because they have the data, the commercial departments have the data to answer these questions. So I think one way for them to use it for the planning process is to see how they can use our approach, our methodologies, and the large amount of data that they have to better these predictions in the context that they are working in. Now, that just answers the prediction for unelectrified, but looking at like growth, I think it still aligns pretty well because they can still leverage the data that they have to sort of tease at these questions using the methodologies that are being proposed. So I must see it as us sharing these methodologies, but them leveraging the richness in their data to answer these questions better than we ever can.
And what do you see, Simone, as the potential challenges even in other countries beyond where you have done your work? Any thoughts on other landscapes that you would care to sort of conjecture?
I'd say we focused a lot on Kenya, but at least from our initial analysis of Rwanda, we're observing that different landscapes, different countries have different consumption profiles, different behaviors. So one of the challenges, like when we think about approaches that are suitable across multiple countries, multiple regions, how do we ensure robustness in our processes given the specificities of each of these countries? Not sure that we have a good answer yet, but I see that's a challenge that
Oh, and there's one more question, in fact, on the chat. Is there any plans to grow energy consumption prediction to make it diurnal? I suspect the question is how much of the consumption in the daytime and how much in the nighttime? And also the other question was, how do you think such methods will apply with electric vehicle electrification and also with distributed generation? So that's a whole bunch of questions, Simone, and if you go ahead.
Yeah, that's a whole bunch of questions. I'd say for the first one, the different patterns, it's really based off of the resolution of the data that comes in. Right now, we have, at least in the case of Kenya, we had postpaid monthly bills. In Rwanda, we are looking at prepaid. So based off of the resolution that we get for the data, that sort of influences how we design our methodologies. So it's somewhat hard to get this like diurnal patterns if we don't have a good way of grounding what they actually look like in data. But if we can get the data, I'm sure there can be some research efforts there. So far, I mean, with respect to like electric vehicles, at least our approach, we have been somewhat agnostic to the, if I may say, appliance, source or what's consuming the electricity at the user's end. We've sort of just been looking at what that amounts to. But I know that some of our colleagues are actively working on understanding demand from electric vehicles. I think June is in the e-guide initiative. So I think that's somewhere in the horizon. Am I missing any other question?
No, that's it. And I think the other question is of distributed generation, and some of our sort of e-guide effort is addressing mini grid consumption as well.
Yeah.
I missed a question from Dr. Idrisu, and I think it's a very interesting and important question, is what is the level of governmental and stakeholder engagement to have their buy-in? And I will hand it to Simone, but like your early work, is co-authored by Samson on Deck from KPLC. But if you want to, I think if you want to take that as well, Simone or Jack.
Yeah, I think it's quite important to have the utility involved. Like you mentioned, our first work on just the consumption study. Samson is a co-author on there, but also in terms of getting the data, interacting findings, we can't do that without the support of the utility in any country actually. So that's been quite critical for us to do this study.
I can add there that about a month ago, Simone, did present at the SC for All webinar. And there are others who are in the sort of more in the line of supporting country developing plans, supporting geospatial work, supporting technology choice. And those have been the first quote unquote beta users of this work. So indeed, we talked to quite a bit of stakeholders and to help shape how to publicly share this data. And, Simone talked about the API as well. So over to you, Jack, if you had any comments on sort of stakeholder role in especially the work you showed on smallholder irrigation using solar, and also our current stakeholder in the camera work you are doing.
Well, I can currently say, I can say that having a government help with this would be beneficial. Increasing the number of kind of camera systems that were out and and collecting would be beneficial. I can say that also going through any sort of problems that you may have with capturing the images of different people along the roadside. But other than that, I don't have a whole lot to say on.
I was thinking that perhaps the governments do have their vehicles and could use this to map quality and quantity of infrastructure and get a sense of the kind of things that are not. So a utility might already know where its wire is, but the water and environment people may not know where the locations of wells or other sort of infrastructure is. So it's very possible that this is something. I do want to highlight one thing perhaps to this question. Let me see if I can share a slide. So for example, the water ministry, and I'm trying to find the slide, here it is. The water ministry, for example, in Uganda has a very thorough atlas, right, of where wells are, where streams are, and how can that be kept updated? How can that be kept digital and shareable? So I think there I do have a comment on the question that Dr. Idrisu had, is that one of the biggest challenges we are hearing from our colleagues in the field is that different entities over the last decade are gathering data, but a mechanism to share that is not yet in place to make it useful and pragmatic. So for that I want to share something. Is when we did gather data in Nigeria, everything was made public, including the raw data download, so that one can actually go to any place, any region, any state. Within the state, it's like a district, it's called a local government area. And when one does that, one can then have literally access to exactly what facilities are, what state of the water point is. It's maybe functional, it may be a borehole, it may be not, and so on. So the ability to also convey is coming through what the stakeholders are asking. Okay, so I want to just Sashi Shekhar as I question, and I think it's for Simone. What are confounding factors in estimating electricity use from daytime satellite imagery? Do some materials, as for example, brick, absorb more solar than others? Do they appear warmer even without electricity use? So it's a question about what you see in the daytime imagery, perhaps roof materials. Over to you, Simone.
So just to clarify one thing, we are associating features in images to consumption at the meter. So the house itself is not necessarily powered by solar. It's just powered by the utilities.
The question was about, is there any roof material that you think may have a confounding factor?
So yeah, right now we see, if I may say, tin roofs being associated, or natural material roofs being associated also with the lower class. We have this more, I'd say, reddish brick-like roofs, larger roofs being associated with a higher class. Again, these are somewhat like proxies for wealth, and there is no like direct link to electricity itself from the roof. So we're just trying to associate that proxy to the consumption. And if I'm able to get at
we can take that conversation offline as well with him. So any other questions or thoughts? Otherwise, I don't see any more questions. I can hand it over back to Lillian, back to Pauline, back to Murugi.
Thank you so much, Prof. Vijay. Thank you, Simon and Jack, for that excellent discussion on how remote sensing can be of value to the energy sector, to Kenya. At this juncture, we want to thank all our viewers and panelists for taking your time to join us in this discussion. It is a pleasure having you. And so without further ado, we would just like to say thank you and also to wish you a great afternoon, evening, morning. Yes, thank you so much.
Thank you all. Bye.